Hey everybody, we're going to take a look at frequency for standing waves on a string today. If I hit begin, you'll notice we have a hanging mass over here, and we're going to hit the fourth harmonic with a string that is oscillating up and down here at a certain frequency. They want to know the frequency the oscillator needs to be set to so that it's able to oscillate to the fourth harmonic of this string. So the vibrating part of your string first has a length of 103 centimeters. So I'm going to say L is 1.03 meters. I'm also going to say the mass of the string is 0.00268 kilograms. And the mass that's hanging here is 2765. So the tension in the rope, I know that the mass mg is pulling down and the tension in the rope pulls up, and this is going to be equivalent. So tension equals mg. So what is mg? That'd be 2.765 kilograms times 9.8 meters per second squared. And so the tension in the string is going to be, let's see here, 2.765 times 9.8. Tension of the string is going to be 27.097 newtons. So I know that the velocity of a wave on a string is determined by the tension and the mass per unit length. So if I plug everything in here, the velocity on our string should be 27.097 newtons divided by mass 0.00268 over 1.03, all that square rooted. So divide that by 0.00268 divided by 1.03. And take the square root of all that. I get 102 for the velocity. So 102.05 meters per second. So if the velocity on the string is that fast, and I want to hit the fourth harmonic, for the record, the fourth harmonic is where, if this is the length of the string, that would be the open note of the string. That is the first harmonic. The second harmonic would look something like this, where there's two antinodes, right? So what would the fourth harmonic look like? The fourth harmonic would look something like this, where we divide this up. We're going to have that as our overall fourth harmonic of that standing wave. So that means that this length would equal 2 wavelengths. So I'm going to take the wavelength. I know that 2 times the wavelength has to equal the total length of the string, 1.03 meters. So that means wavelength would be 1.03 over 2, which is 0.515. Okay, so it's important that we note what harmonic number we're at, because that determines how many waves fit on our string between these 2 points. So this right here is our overall length, and that's equal to, in our case, 2 waves because of the fourth harmonic, right? So let's go ahead and figure out exactly for the velocity of a wave on a string. For a standing wave, it's going to be the, let's see here, 102.05, and that has to equal wavelength times frequency. So I know the wavelength is 0.515, so the frequency is going to be, let's plug this in right here. Frequency is going to be 102.05 meters per second divided by the wavelength, which is 0.515 meters. I get 198 for the frequency, 198.15. And I apologize, I kind of went all over the page here, but hopefully you can follow kind of in order what I did here. But 198 is my overall final answer. Let's plug that in and see if we are correct. And let's erase all this stuff so you guys can actually see what's going on here. All right. My name is Oasters. Frequency is 198.15. We hit submit. Just click on the oscillator to see if your frequency. So I click on the oscillator and my answers are correct. So obviously the goal is to be able to use the equation for the velocity of a wave on a string, tension divided by mass per unit length, making sure all your units match the standard units. And you can actually see the fourth harmonic is where exactly what we drew down here, where two full waves fit in the length of the string. So hopefully that's helpful. If you have more questions, feel free to plug into office hours, or because we're meeting asynchronously on Thursday and Friday this week, perhaps we may have to revisit this in class.